course, thanks to the organizers for bringing us all to this beautiful city. My first time in Natal, really enjoying it. I'm going to be, and also thank the organizers for not just inviting me to speak, but giving me the luxury of a 90-minute talk, which means I can maybe, which means I can give a Blackboard talk and maybe go at a slightly slower pace and so on. Feel free to interrupt me with questions. Obviously, I don't have a specific goal that I need to get to. The idea is to give a sort of an overview of bit threads and then talk about some recent work and work in progress. But again, I don't have a specific goal that I need to get to in these 90 minutes. As an unrelated comment, I'm going to abuse this platform I've been given to promote a trend I'm trying to start in our field, which is, it's not an original idea, it's something people in other fields do, but I think it's a good thing, which is when you write a paper, when you post a paper on the archive, to record a short video, like 2 or 3 minutes, just saying what's so great about the paper, sort of for, you know, and then you post that on YouTube and put the link on the archive, and that just gives people a way to you know, get the gist of the paper, slightly different from reading the print abstract. You can have visuals and so on if that's helpful for what you're trying to explain. And I think it's just a great way. I mean, for me, I learn better like listening to talks and so on than reading papers. I'll read a paper to get all the technical details, but it's but hearing somebody like sitting next to me at lunch and giving me, you know, the quick spiel about their last paper is like, you know, I'll get the big idea way better than if I try to read the abstract or skim the introduction or something. And it's not, you might say, okay, that's going to be a lot of work. To be honest, I'm not really sure how much work it is because it's always my student who's done it. But he says it's not that much work. So you just kind of record yourself giving a little 2 or 3 minute talk on Zoom. If you look at one of my recent papers and follow the link to the video abstract, there's actually instructions there for how to do it and get a nice result with kind of minimal effort. Okay, anyway. That doesn't have to do with bit threads, except insofar as, of course, my next paper on bit threads will have a video abstract. So this talk is about holographic entanglement entropy and different ways of thinking about it. So by now we're all quite familiar with RT formula, and it's taught us, the RT formula and its generalizations have obviously taught us a huge amount about holography and quantum gravity and black holes and so on. And the RT formula is expressed in terms of the area of a surface. And the point of bit threads is you can re-express that geometrically in terms of the flux of a vector field or a number of one-dimensional objects, which are what we call bit threads, in the bulk, subject to some rules. And it's just a new perspective, and I think for something as fundamentally important as the RT formula, it's always good to have new perspectives. And I'll give a couple examples of things that you kind of learn or you think about because of this different way of expressing the RT formula. And then, of course, there are, of course, many generalizations, as I mentioned, of the RT formula, and then one wants to generalize the bit threads to those generalizations. And so that's what this work in progress is about, specifically the quantum generalization. So if you take into account bulk quantum effects, so then you replace the RT formula with the quantum extremal surface formula. I'll write it all out later in the talk, but and then the question is, how do you adapt the bit threads to incorporate bulk quantum corrections, meaning entanglement of the bulk matter fields? And so that's something that my former student Andy Rolfe, who's now a postdoc in Brussels, wrote a very nice paper on a few years ago. And then we're sort of extending that work with Andy and Sriman Kasireddy, who's a graduate student at Weizmann and was a master's student with me at Brandeis. Okay, so let's just start with the initial RT formula, which is just classical Einstein gravity. And it's applicable to static spacetimes. By the way, is this visible from the back, or should I write bigger? It's okay. All right. And of course, what we want to do is to release each of these assumptions and so on, and we'll talk about that. Static here could be actually static. Actually, it's enough to have this slightly weaker version, which is just instantaneously static. Instantaneously, which means that you have a moment of time symmetry, and then you're working on that moment of time symmetry, and so you get rid of the time direction. But it doesn't have to be, you could have a time-dependent space-time away from that moment of time symmetry. Okay, and then the formula, which I'm assuming is probably not new to anybody in this audience. So here's my boundary, and I pick some bulk region, and then the idea is to find a surface in the bulk that is homologous to your chosen boundary region that has the minimal area. So I'm actually going to work, it's slightly more convenient to work in terms of bulk regions. So this is your formula. I'll explain the notation in a second. It's good that I'm starting with a fairly simple case where presumably people are familiar because I'm throwing some notation at you. So this is the set of bulk regions such that R intersect the boundary is A. Okay, so this is my sigma, and that's my boundary. So R that you're minimizing on has to meet the conformal boundary precisely on A, and then this D slash thing is the bulk part of the boundary of A. So it's this. This, by the way, is an Icelandic rune, which in tech you write is \ETH. Okay, so and it'll just be convenient to talk about the region instead of this. Often you write it like minimum over surfaces subject to a homology condition. This is just a way of rewriting the same thing. So this surface D slash R, because of this condition, is homologous to A. Okay. Oh my God, look at that. The other one comes down automatically. Amazing. And look, there's chalk. Oh, except that, of course, all right. Change my mind. Okay. Change my mind. Okay, so bit threads. I'm going to have to erase this. What you do is you put into the bulk a flow. So that's going to be a divergenceless vector field. And the flow lines are what I call bit threads. So here you can rewrite this as a maximum flux on A of the flow. And what is a flow? A flow on a Riemannian manifold is a vector field that satisfies these two conditions. Its norm is bounded above by 1/4 G Newton, and it's divergenceless. Okay, so divergenceless just means that the flow lines don't end or begin in the bulk, and this norm bound means that they can only be packed together in this, at most in this particular Planckian density, and then when you carry out the maximization, the bottleneck, which is the minimal homologous surface, is what prevents you from adding more, and so at that point the threads are actually maximally packed on the minimal surface, so they actually saturate this bound on the minimal surface. And this equality is guaranteed by a theorem. So it's just a fact about Riemannian geometries. Okay, and so just a couple general things about bit threads. One is that so at first there seems to be a nice symmetry between these things. You know, you're minimizing, you're maximizing, but you have to be a little bit careful because they are qualitatively different. And one of the big differences is that whereas the minimal surface is typically unique, if you fine-tune things, you can have a situation where maybe there are two competing minimal surfaces that have the same area, but you know, generically it'll be unique. Whereas this is never even close to unique because it's only on the minimal surface that that the threads are maximally packed, or if you want the norm bound here, is achieved. And away from the minimal surface, there's just all this freedom. In fact, there's so much space out here that I could even do something silly and just add things that do this or things that do this without changing the flux through A, okay? Or things that do this out here, because there's a ton of space out near the ADS boundary. Okay, so that's one thing, and that freedom actually indicates something physical, so I'll give an example in a second. Another difference between these two formulas is that this one defines what's called a convex program. So the set of vector fields has a natural linear structure. You can add vector fields, multiply them by a real number. And these conditions are convex conditions on the vector field, and this is a linear objective that you're trying to maximize. So this maximization problem defines a convex program. And that's a mathematical fact that's very useful when studying these things. Potentially, although I haven't seen somebody doing this, I could imagine that it could even be useful numerically for maybe finding RT surfaces in some complicated geometry that lacks symmetries. Certainly that's something that in image processing they use basically an equivalent of this to find minimal surfaces, because turning it into this kind of convex program is useful. Okay, but in the physics sense, let me just give a, so, you know, one of the nice things about the bit threads is that they, I think they translate what's going on physically with the entanglement a little bit more transparently than the minimal surface. So at some level, one way to think about this is that you've essentially created so you can think of each thread, each flow line that connects 2 points on the boundary, and let's quantize them so that each one has cross-sectional area of 4 G Newton. Then of course it's not true. So you might have thought, oh, okay, now I see what's going on with the entanglement. It's that this point is entangled with this point, and this point is entangled with this point. So that's not right, because entanglement in a quantum, this is a strongly coupled quantum field theory. It's much more complicated than that, and you can see that it's not right precisely because of this freedom that I was talking about. You know, so if this is a maximal flow, there's a maximal flow that looks like this as well, and so it's better to think about a maximal flow configuration as like a distillation of the boundary, where you're just choosing to distill this entangled state of two parties, in this case A and A complement, into a set of Bell pairs. And of course, there's many, many ways to do that. After you've done the distillation, then maybe you have, you know, this degree of freedom is in a Bell pair with this degree of freedom. And it does not mean that the state you started with only has bipartite entanglement. The state you started with is probably very, very complicated, has all kinds of different, you know, multi-party entanglement and so on. But after you've done the distillation, you've kind of like gotten rid of all of that stuff. So I think this distillation way of thinking is kind of useful. And of course, one can talk about, well, how do I use bit threads to probe multi-party entanglement? And that's very interesting. That there's a bunch of papers by my former student Jonathan Harper on that. I'm not going to talk about it in this talk, but it's a very interesting question. Okay, let me just give an example of how the information theoretic structure is reflected by the bit threads. And let me just do like a slightly different cartoon. By the way, I mean, I'm going to draw cartoons, but everything I say is completely dimension independent. Limited, I mean, the cartoons are limited, of course, by my drawing ability, but the math here is completely dimension independent. So, yeah.
Any specific way you can get this theorem from tensor networks or tensor network formulation?
Okay, so people have not, as far as I know, really thoroughly studied bit threads in tensor networks, which is, but I think one could. I think the problem is actually that a general tensor network, if you don't put some conditions on the tensors, you know, a lot of, is not necessarily really analogous to a gravitational space-time. I mean, there's a very loose analogy where you can compute a bound on the entropy in terms of a min cut through the tensor network, and of course that there is this theorem, this max flow min cut theorem, has a graph theory analog, but that's just a bound. Okay, it's not actually calculating the entropy. The entropy could be far less than that bound. So presumably you need to put other conditions on the tensor network to actually achieve that bound. That's what these special, like happy code and so on, are designed to achieve the bound, and random tensor networks do that. And so presumably in one of those tensor networks that achieves the bound, one can run the same arguments, but I haven't seen it done quantitatively. Bartek.
It's okay. You already answered my question of random. It's on now.
Okay. I kind of wanted to back on that question and ask about random tensor networks. So there, it seems like it should make sense to talk about bit threads. Yes.
Yeah, I think so. I just then you have to decide: do the threads live like in the network before I average over the ensemble of tensors, or after? So, I mean, I think it's an interesting question, and you know, somebody should write a paper. Maybe it's an easy paper. Maybe it's a hard paper. I don't know, but yeah, it does seem like kind of begging to be done. I agree.
Yeah. So this is a distillation picture. This is a general moral statement, or you can make this precise that there are protocols that distill information associated with every flow, or
it's an
yeah. How precise can you make this, other than the fact that the entropy? I mean, like when you distill, there's an issue of how you distill and how much can you distill relative to the full von Neumann entropy, etc. So, is that an issue here? Or?
Yeah. So if one wanted, so I think at the classical level that's not an issue, because at least like the leading in 1 over G Newton entropy, which is all I'm getting so far, I think that's all distillable. So I think it becomes a more interesting quantitative question when you have like multiple parts, and then you're trying to distill the multi-party entanglement. And there we have, so in a paper I wrote a long time ago about about multi-party entanglement with bit threads, we had a conjecture based on this distillation idea for the multi-party entanglement structure. And that conjecture was sort of pushed back against. So the conjecture was that if you divide your boundary into 3 regions, so then you can prove a theorem which is like a more powerful version of this one, where you can max out all of the entropies with threads like this, and then these threads correctly count, so you get the entropy of A by this total number, or AB from this total number, and so on. And the conjecture we made, which was also based on some tensor network evidence, was that basically there's a distillation that turns this state into just Bell pairs. Okay, that there's not, that the amount of tripartite entanglement like GHZ or W states or whatever more complicated things is sort of subleading. People have written papers arguing against that. I mean, I should say it was a conjecture. We didn't have like very strong quantitative evidence for it. But Chris Akers and Pratik Rath wrote a paper giving an argument against that. I think that argument is wrong, but we can argue about that. So it's still kind of open. So you can try to take this, anyway, the lesson is that you can try to take this thread picture and if you take it seriously, derive from it quantitative statements about this distillation. Any other questions? Yeah. So what I would have said, so of course, if you have an entangling surface, then your entropy is divergent. So one thing you can do is you can introduce a regulator, and that will make the entropy convergent. So one thing you can do is, or make it finite, so you can like introduce a little buffer and cut off a little piece of your bulk on that boundary. And then that will be finite. Then then you actually have, so you basically force the Hilbert space to factorize. You've made it so that it now does factorize. Another thing you can do is you can look at a quantity that's intrinsically finite, like a mutual information. And you can use the threads without a cutoff to calculate a mutual information for separated regions, which is an intrinsically finite quantity that can be defined in a continuum field theory in terms of a relative entropy. So actually that segues into what I was about to say about computing mutual informations, but you look like I didn't answer your question. Yeah. 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 You've basically taken this and turned it into like a multi-boundary wormhole, right? In a multi-boundary wormhole, as long as you take entire connected boundary components, you don't have this issue. Like everything is finite. All the entropies you compute are finite and so on. And so this is just a regulator that turns your bulk into a multi-boundary wormhole. Okay. Yeah, maybe we should talk about that later. I'm not exactly sure what that, I mean, if you don't have a regulator, then of course you just get infinity. If you have a regulator, then yes, the value you get will depend on the details of that regulator. As long as the regulator is implemented geometrically, so the regulator has a bulk dual, then, and as long as in the presence of that regulator the RT formula is correct, then this formula will be correct because it's just a theorem. So I think, yeah. Yeah. Any other questions? Okay, so yeah, so if I have a multi-boundary wormhole, and again, this is just for cartoon purposes. You know, I mean, I can of course use the threads to compute S of A, then I'll have a flow that goes from A out to these two, S of B, or I can compute S of AB, and that way I can compute mutual information, and the mutual information is roughly speaking, we'll have like a classical and a quantum part. So there'll be some classical correlation between A and B, because once I trace out this, then I have a mixed state. So there might be some classical correlation. There might be some quantum entanglement between them, and that's all shown by the thread. So when you look at a thread configuration for computing S of AB, so you have some flow that's like this, then there'll be some freedom. If it's the case that S of AB equals S of A plus S of B, then actually there won't be any freedom. They'll still be freedom out near the boundary and so on, but in terms of the number of threads connecting A to the complement versus B to the complement, that'll be locked down. But if the mutual information is non-zero, then you'll be able to move some threads back and forth. And the threads that you move back and forth are representing classically correlated bits between A and B. And then you can add threads that connect A to B directly, and those ones, they can switch orientation. If I'm computing S of A, then I would have it pointed this way. If I'm computing S of B, I would have it pointed this way. And each one of those, because of this switching orientation, contributes double to the mutual information. And those would represent entangled qubits, okay, Bell pairs, okay? So anyway, this is just the kind of thing that you can, and then you can do things like understand the proof of subadditivity, the proof of strong subadditivity, which we know how those things work in terms of surfaces, surface areas. We have these cut and paste arguments that that show that the RT formula obeys those properties, and there are proofs using bit threads that involve basically moving threads around, like I just did here, and counting the number, and so you can calculate things like the mutual information, the conditional mutual information, and so on from the bit threads. Okay, so that's just to give a little taste of what the kind of intuition you can get from bit threads. And then, as I mentioned in passing, there's many generalizations of RT. And I just want to list them so that you're aware they exist or have been studied. So the first one is the covariant or HRT version. And let me just very quickly, so this is a paper I wrote with Veronica Hubany in 2022 about covariant bit threads. And the picture there is that, and again, this is very much limited by my drawing ability, so I'm just going to go down. So this would be like a cross section. So this is now time. And this is some ADS space. And here's my region A on one boundary and A complement on the other. And then A will have a domain of dependence on the boundary. Maybe I can attempt to, so if I just do a picture of the boundary, so I have some boundary slice, and I have some region A, and then I have its complement, and then I have the domain of dependence of A, and the domain of the complement. And the point is that, okay, putting aside subtleties regarding the regulator, like what's going on at these points here, basically the entanglement entropy is actually a function of the domain of dependence. In other words, if I picked a different A that had the same domain of dependence, it would have the same entropy. Again, modulo subtleties at the entangling surface itself. And so you want a formula if you're going to be counting threads. So now if this space is the bulk, okay, and this is the boundary, then I'm obviously going to want some threads that go from D of A to D of A complement through the bulk. But it should really be, I shouldn't really refer to A itself, the spatial region. I should just refer to the domain of dependence, ideally. So if I really want it to be fully covariant, okay? So I have some boundary domain of dependence for each of them. So d of a. So let me just even get rid of a, because that's going to be irrelevant from now on. Okay, and then you're going to send in threads that you're going to be maximizing the flux. So you're going to be maximizing the flux. This part is the same, except it's now integrated over d of a, and this field I'm calling capital V. Okay, and then you have to have some notion of a covariant flow. And I'm not going to derive this, but you can derive what the rule that I'm about to give you, which is, first of all, you're going to keep the divergence constraint, which I think is kind of natural. You want the same number of threads like connecting, like that leave A entering a complement. You're going to need some boundary conditions. So the boundary conditions are going to forbid threads from going into the, basically from ending on this region here. So they can only begin and end on these regions. And then the hardest part is the norm bound, because you want something that's Lorentz covariant. Okay, and it's not actually easy to make a norm bound, because if you do something like this, and V is just, and if V is just now a vector in Minkowski space, on the tangent space, of course, a norm bound like this allows V to be arbitrarily large if it's like close to the light cone, right? So you could have like huge fluxes. So that doesn't seem right. And it turns out that the right thing to do is to put a non-local norm bound. Which basically looks at the integral of basically the total number of threads seen by an observer. So you have some time-like observer who's living somewhere in the bulk and counting the threads. As they live their life, they see these threads, which are, they're still one-dimensional, so they're sort of instantaneous in time. And the total number that the observer sees cannot exceed 1/4 g-Newton. There's a formula, I know it just sounds like words, but anyway, there's a formula you can write down that enforces that. And then what happens is that when you actually go and maximize, subject to those constraints, the threads find the HRT surface and the entanglement wedge. So somewhere here, and just to emphasize, I'm not putting this, so this is my HRT surface, I'm not putting this in as an input. The existence or location of this surface is not part of the rules here at all, but the threads will find it as part of the maximization, and they will all go through it. If you did anything else, it would be suboptimal. You would not be maximizing the number of threads, and they stay within the entanglement wedges. So you can prove that. Okay. So, which is to say that there is a covariant generalization that works, and it's, in my opinion, I mean, I'm biased, I guess, but it seems fairly elegant. And again, it's a convex program, and so I could imagine that maybe for numerical purposes, if you have like a fairly complicated spacetime without symmetries, and you're just trying to find the HRT surface, this might actually be a useful algorithm. Just because convex programs are things that there are very, very fast numerical algorithms for solving. Okay, any questions before I talk about other generalizations? About what? Oh, mutual information, yeah.
So if you put constraint, if you try to solve for a flow with the constraint that the mutual information is 0, then you should have only, this flow should go from A to B only, right? There shouldn't be, it should be strained to this other part, to the right part.
If you're in a situation where the mutual information is 0, then first of all, there's not going to be these, and then the numbers here will be fixed. So this number will be S of A, and this number will be S of B, and you won't be able to move them from one to the other. Is that?
Yeah, I think I made a mistake. So it was actually not 0. It's Okay, yeah, I agree. Yeah. Thank you.
Okay, some other, okay. So I mentioned multi-party entanglement. There's Rennies, so there's a way to use bit threads to compute Rennies, which is something that when I have some time, I'll write up. It's nothing, yeah, I'm happy to tell people about it. It works out very neatly. There was something else. Oh yes, and higher derivative corrections. So, if you're not in Einstein gravity, but you're doing string theory, you have alpha prime corrections or whatever, then your RT formula gets corrected. And so I wrote a paper, I don't know, 7 or 8 years ago with Andy Rolfe and Jonathan Harper on how to implement higher derivative corrections with bit threads. And basically, you correct this, you get a more complicated norm bound. So you keep it divergenceless, but you get a more complicated norm bound that depends on the geometry. It's actually fairly complicated. Here, in this particular case, I wouldn't necessarily say that we found like a very elegant, general formula. So there may be something we're missing there. Okay, but the main thing I want to talk about, this is just to, as an advertisement, is quantum corrections. Okay, and of course, one can combine these things, so one can do like quantum covariant and so on. I'm not going to do that today. That's something we're thinking about. But already the static quantum corrections are interesting. So I'm just doing one at a time. I'm not also turning on higher derivative corrections or Rennies or anything. Just doing RT, Einstein gravity, static, but including quantum corrections. And how do you include quantum corrections in the RT formula? So you have this quantum extremal surface formula by Engelhard and Wall, which is like this, which is actually very similar to what's there. But you replace the area term here with the generalized entropy. And the generalized entropy is a complicated beast. But for our purposes, we'll do like a cartoon version of it because that's already interesting enough and rich enough, which is that you simply take that area and you add on the entropy of the bulk region to it. Okay, there's a lot more that can be said about this, and I guess Sean is giving a talk this afternoon, which is about the generalized entropy. So these two equations have complications. So it's this QES formula is only true for some class of bulk states. So there are sort of exotic bulk states that have very weird Renyi spectra that are not the kind of states you would typically find in nature, for which this formula is not correct, and there's a more complicated formula involving these things called smooth min and max entropies and so on. But there is a class of states for which this is correct. When I say states, I mean bulk quantum states. This thing also, receives corrections and so on, and there's a very complicated story there. But for the purposes of this talk, this is already interesting enough to study as it is. Okay, so I'm just going to take these as given. There's interesting facts about this S-gen, for example. Again, modulo complications that I don't want to go into, which is that actually these two terms are not actually strictly well defined once you take into account quantum effects. So the bulk entanglement entropy, of course, needs a cutoff because there's an RT surface which is separating R from R complement, and so there's a UV divergence there. So this is actually a UV divergent quantity, and but thankfully G Newton also depends on your choice of cutoff. It runs, and the lore, which has been checked to some extent for specific field theories, is that the sum is going to be independent of the choice of cutoff, even though the two terms separately are not. So that idea goes back to Susskind and Ulam from the 1990s. Okay, so we're going to take this formula as a given, and we're going to ask how you change the bit thread story, again, just starting from this one, forgetting all of this interesting stuff, how we're going to change this to accommodate this correction. And in particular, I mean, one question you might ask is, you know, which of these or both, or are both of them going to be changed? Somewhere you're going to need to change this formula to incorporate this bulk entropy term. And the question is that going to enter into the norm bound or the divergence-less condition? Okay, so one way to attack this problem is to look at a model where actually you do have a geometrical formula for this term. And those models are doubly holographic models. So so as a starting exercise, we're going to look at double holography. The last time I gave this talk, the talk came to a screeching halt when I tried to, because it turns out double holography is like something complicated that people have different opinions about. For me, it's just a toy model, and I'm just interested in the geometrical aspects, because for me, what double holography is a situation where this has a geometrical expression. Okay, so double holography means that the bulk matter fields are a large N holographic theory. You know, whether there are such quantum gravity theories, whether it obeys swampland conditions, whether there are top-down constructions, these are all very fascinating and important questions that are totally irrelevant for my purposes. Okay, so so that means that we can use RT to compute this bulk entropy. So what's the picture? And apparently the way I draw double holography is different from the way most people do, so sorry. That might be quite confusing. So this is that picture just tilted on the side. So here's it's a time slice of the bulk, and I'm going to have a region of the bulk, a region of the boundary, sorry. And I want to compute the entanglement entropy of this region. And the reason that I drew it tilted is because there's another dimension, which is which is the bulk for the matter fields living on sigma. So this I'll call sigma tilde. This is the second bulk. Okay, so I have my matter fields living here. They have a dual description in terms of this one higher dimensional sigma tilde. And if I have some bulk region, this region is not homologous to A, but just consider this bulk region, and I wanted to compute its entanglement entropy, I would use the RT formula in the second bulk, so I would get some minimal surface that hangs down into sigma tilde. Okay, now, and I guess a lot of people got confused about what this thing is. Just don't worry about it. It's not important. Okay, so you can think of it as like some confining wall or something, or it's like a Poincare horizon that's very far away. It's not going to play any role. in what I'm saying. It's not, there's no theory living on here. It's not like a second CFT or something like that. Okay, so now what we wanted to do was not compute the entropy of this thing that I just drew. What we wanted to do was compute the entropy of some region that's homologous to A. So I have some bulk region R. So this is my R, and that's the boundary of R. And then I want to know what this is. So I apply the RT formula. So yeah, this, in fact, I should write it. This is going to be the minimum over R tildes of the area Okay, so this is my higher dimensional Newton constant. R tilde is a region in the second bulk, so it's like a shower curtain that hangs down, so there's some surface here in the second bulk whose area is going to tell me S of R. Okay, so then in the end, this thing, I'm adding these two terms, and so I get the area of this. So this thing here would be R tilde, and this thing is my D slash R tilde. So I have the area of the shower curtain, and then I have the area in the higher dimensional thing divided by 4G Newton tilde, and then I have the area of this surface, which is my just regular RT surface divided by 4G Newton. Okay, are we okay with this just purely geometrical construction? Okay, and now I can switch to bit threads, and you can easily derive what is the bit thread version of this formula that adds together, that combines these three things. And you won't be surprised to learn that, of course, it involves, since here I'm computing an RT entropy, there are going to be bit threads in the second bulk. Okay, but there are also going to be bit threads in the first bulk. And how do those relate to each other? So it turns out that that they do relate to each other. They do interact, actually. So when you go through the math to prove the analog of that theorem to get the bit thread formula, you find that the threads actually are allowed to move between the two bulks. Okay, so this is the formula you get. Let me just, well, no, I'm going to need that. Okay, so you get this. Let me write it here. So first of all, I'll just copy this. So I'm going to have a flow in my first bulk, and I'm going to have a flow in my second bulk, and they're going to be related by the following condition. Well, first of all, I'm going to have, of course, these two norm bounds, as you would expect, but the thing that changes is the divergence constraint. So no longer is it true that the divergence of V is going to be 0. Instead, the divergence of V is going to be the boundary value, the boundary flux of V tilde. Actually, minus that. Okay, so what's going on here? What's going on is that a thread is allowed to, thread comes out of A, it's trying to make its way to A tilde, to A complement, okay? And it can just stay on the surface, or it can dive in and cross through the shower curtain. And you're just trying to maximize the number, so you're probably going to do both. Okay, so what it looks like on the surface is that some of the threads went across like this, and others just dived and reappeared. Okay? So you're going to get, when you maximize it, you're going to get some number of each, and the number of each is going to actually be these two terms. Okay? Because the ones on the surface are, of course, going to be maximally packed. If they weren't, you would just add more. The ones that dive down, that go subterranean, are also going to be maximally packed on the minimal surface in the higher bulk, because if they weren't, you would just add more. Okay, so you actually have a clean distinction between the classical threads and the quantum threads. And each one is responsible for one of these two terms. Okay, so it's a very, I think it's fairly intuitive, and the lesson is, because we don't just want to do double holography, is that you have to relax the divergenceless condition, and you don't touch the norm bound. Okay, so that's the lesson we're going to take from this doubly holographic model. Okay, yeah. Yeah, so there will be freedom in the positions, because as usual, they're at least away from the minimal surface, there's a fair amount of freedom. So again, there's nothing, just like there's nothing here, I emphasize that there was nothing special about these 2 points. It's not that these 2 points are the ones that are entangled with each other. Here, it's not that these 2 points are special. I could have moved things around so that it re-emerged at a different point there. But the ones that are close, so there's going to be a lot, because this is, of course, a UV divergent. S of R is a UV divergent quantity, so there's going to be a ton of threads that just jump right across like that. And those ones, there'll be less freedom, because they're just so packed together. There's like many, many, many of them that are just doing this. So they tend to jump like directly across.
Is there an understanding from this picture of the fact that the generalized entropy is better behaved under normalization than each of the two pieces?
At least a qualitative understanding. So basically, and you can already see it, if you squint at these, they look like they're just going across, right? And so that's essentially under changing the UV cutoff length scale. If I make the UV cutoff length scale larger than the separation between these, then you stop thinking about it as a quantum thread that jumped, and you just think about it as something that went across, okay? But the finer your microscope, if you make the UV cutoff smaller, then you resolve that actually, oh, it turns out this was not continuous. This one actually jumped. And in fact, yeah, and in fact, you can think of any continuous one as one that's actually just like doing a lot of jumps, if you want. So basically, as you change that UV cutoff, you're moving this boundary of the second bulk up and down, and you can always accommodate, I mean, as you do that, you of course change G Newton, so you change the norm bound on that first bulk. And so that accommodates, because you would have said, oh no, this is terrible. There's like threads that I had here, I'm not gonna be able to do anything with them if I lower this boundary. But what you do is, as you lower it, you also change G Newton to relax that norm bound and allow them to go across. Okay, this is so, this is at the level of intuition. I think doing it carefully requires, you know, sort of, thinking very carefully about exactly how G Newton is varying with epsilon. But I think the picture says that it's going to work, basically. Questions? Okay, so this is great. Like, we have a formula, okay? And if the formula, I think, makes physical sense, we can go and do all the things we did here, you know, calculate mutual information. But the thing is, that wasn't really what we wanted. What we really wanted, we only wanted double holography as a toy model to build our intuition. And what we really want to know is, what is the general formula? So if I just go back to this, what am I supposed to do? Apparently, I'm supposed to relax the divergence constraint in order to reflect the bulk entropy, because clearly what's going on here is that it's the fact that there is entanglement between this part of the bulk and this part of the bulk that is allowing this guy to jump from here to here. But I need something more quantitative, okay? So, so to be more quantitative, I need to rewrite this formula basically in a way that gets rid of the second bulk. So how would you write it if you never knew about that second bulk? Well, the key is going to be looking at this thing, and so here we have the boundary flux, okay? And what is the relation between the boundary flux and the entropy and S of R? So we have that for any region, because we're going to have to go back to regions. This was a nice local thing. We're not going to get a nice local thing anymore, because now S of R is just some non-local function of the set of regions. Okay? So we need a non-local divergence constraint in terms of this non-local function. Well, you can easily see the following observation, that the integral over any region of this n tilde dot v tilde, n tilde, by the way, is the normal, the unit normal here. So let me draw that. So this is n tilde. So that thing is bounded above, okay, so for any region R is bounded above by S of R. Okay, so you can't put more flux into a region than the entropy of that region, because of this theorem that the maximum amount of flux is the entropy of the region. Okay, so this is just essentially from the definition of S of R. Okay, you also, there's also a lower bound that you, if you try to make the flux go the other way, like instead of going in, coming out, you get the same bound. So actually you have this. Okay. Now, it turns out, okay, so then we can have a guess for a general formula. So for a quantum flow, that first of all, of course, we're not letting go of this one, and for any R, the integral of the divergence So here, all I did is, this is a fact we know about the second bulk, and I rewrote it using this equation to get rid of the second bulk. The whole point being that this thing now has a chance of being applicable outside of double holography, because it only involves ingredients, it only involves my flow on the first bulk and S of R. Okay? Okay, so you can show that, so I mean, so far this has just been building intuition, but you can show that this is actually correct, that with this definition, you do get the right answer. So this is the max over quantum flows V of integral on A n dot V. So basically you have a theorem which is like that theorem, but just more complicated because it on the left-hand side you have the QES formula, and on the right-hand side you have this more complicated definition of a flow. Okay, so I get to erase that. Okay. So I think what we need to do is to like build up a little bit of intuition, right? To understand what is going on with this, this constraint, this divergence constraint. Like how should we think about it? Let's look at a few examples, okay? Okay, so let's just look at a few point particle examples. So let's say the bulk entropy we're looking at is just between point particles, okay? Of course, a lot of bulk entropy is not of that form, but let's say you know, on some background, you just add some point particles where you've designed some entanglement between them. So, well, the first would just be a Bell pair. So, let's say I have these 2 points that happen to be entangled in a Bell pair. Then what am I allowed to do with this, given this constraint? And let's say the amount of entanglement is equal to 4 G Newton, is equal to, is equal to 1 in whatever units. Okay, so basically I just have one thread beginning and ending on these things. So I can have a thread ending. By the way, I can always have just del.v as 0. That's always allowed. That's not going to be your maximizer, but that is always allowed. So I can just have nothing happening. It's not very interesting. I can have a thread ending on one of them, and that'll satisfy the constraint for this one and for this one, but not for the 2 together, because the 2 together are in a pure state, so the right-hand side is 0. So if it ends there, it better begin on the other one. Okay, so that's natural. It just says that when you have a Bell pair, any thread that ends on one has to begin on the other one. Okay? So you don't have threads that just like vanish into thin air. Okay? But what about if you have a more complicated entanglement pattern? Like let's say you have a GHZ on three parties. So then you can have a thread entering one, and then it has to leave one of the other ones. You can also have fractions, by the way, because this is everything is continuous and convex, so it can always take convex combinations of these. So I could have one coming in and then half coming out here and half coming out here, etc. Okay? Now, if I do a 4-party GHZ, so that's a situation where any 2, so with GHZ, any subset has the same entropy, let's say entropy 1. So a single party has entropy 1, 2 parties entropy 1, 3 parties entropy 1. The whole thing entropy 0. Okay, so now, this was part of this 3-party thing. So now if I have a thread coming in, it has to leave somewhere because the total thing is in a pure state. But once I decide where it's coming out, I can't do anything else. It blocks the other 2. Okay? So I could have this one coming in here and leaving here or leaving here, but if once I put these on, the other 2 can't do anything. A different kind of 4-party state is a perfect tensor. Where the entropy of any 2 parties is equal to twice the entropy of any 1. So that it gives me more freedom. So when I have a thread coming into 1 and then leaving through 1, now I can actually, at the same time, have threads coming in and leaving the other ones. So actually and this is general, so an n-party GHZ, you just have one thread coming in and it blocks everything else. One thread coming in and leaving and it blocks everything else. Perfect tensor with any number of parties, you can fill them up. Okay, so you can have them coming in to all, and you can have them coming in to half of them and leaving the other half. Okay? Now, and then you can keep studying other, whatever your favorite 17-party state is, and look at all the pretty patterns of threads that are allowed by this rule. But this is just to give an idea of what's going to be going on in the bulk. One thing that's kind of interesting is that you can ask which ones of these, so if you look at this bell pair, okay, this looks a lot like basically there was a secret like wormhole connecting, like a little Planckian wormhole that actually connected this to this, right? So you can imagine, so anytime you have bell pairs in the bulk, you can just imagine that they're connected by little Planckian wormholes, and then you can apply your RT formula or your bit thread formula as if that was just classical, right? And that's great, and that works also for this one. And also for this one, where the wormhole is now just slightly more complicated. So here you would have like 4 things joining. And if you make a little wormhole like this with 4 openings, then you will see that actually you have the same set of rules. You're reproducing this rule just geometrically. Well, all I did is I just went back to double holography, right? This is, you can think of this as being your second bulk if you want. What's interesting is that you cannot do it with this. Okay, so this one cannot be represented geometrically. It's sort of truly quantum. So there's no wormhole that will give you this rule. Okay? So this is the only one of these examples that is truly quantum in that sense, that it can't be turned into a classical cartoon. Okay? Any questions about those examples? That will give you this, that will reproduce this rule. I urge you to try to find a way to draw a wormhole connecting 4 points that will give you this rule that if I have, let's say, some flux coming in of into one and leaving out of another, it blocks the other 2. You can actually prove that it's impossible. And the way to prove that it's impossible is because you have this entropy inequality that applies whenever the bulk is geometrical, which is obeyed by these examples and is not obeyed by this example. So some kinds of bulk entropy are geometrical and some are not, are like fundamentally not geometrical. I think Bartek wants to.
I just want to advertise my talk tomorrow because tell me if I'm wrong, but I think that the class of states that cannot be represented geometrically this way are exactly the ones that I will be trying to discuss tomorrow. So
yes, exactly.
So it's like exactly the subject of tomorrow's talk.
Yes, exactly.
So since this arose some intrigue, then that's that's good.
Well, I think my experience says actually that any GHZ state should be somewhat representable, but we can let this discussion.
Okay. All right. Yeah. Okay, so I mean, the truth is that three-party states, entropies, yeah, let me actually use this as an excuse to make like a broader comment about this whole program, which is that the only quantity that we're calculating on any of these boards is a von Neumann entropy. And that is kind of a crude tool for understanding the structure of a quantum state. It gives you some information, but for example, it cannot, if all you can do is compute von Neumann entropies, you cannot distinguish between a GHZ state, a W state, or just 3 Bell pairs. Okay, I mean, they have the same entropies up to an overall scaling. Okay, so that's the secret reason. So actually there's this question about whether a GHZ is actually geometrizable or not. But to answer that question, it's just not going to be enough to look at entanglement entropies. You're going to need something more refined that is actually going to know about whether it's a GHZ state or a W state or 3 Bell pairs or something else. So I wouldn't necessarily take this as like a real deep lesson. This is more a statement about the fact that this is geometrizable is more a statement about the crudeness of the tool you're using to study the nature of the entanglement. And that tool only sort of becomes really distinguishing when you get to at least 4 parties.
And sorry, I again want to advertise something, because the statement you just made that it's not clear whether the GHZ state and free parties is geometrizable and that we don't see it from the entropies is something that I will emphasize tomorrow. So if you found that thought intriguing, then please hold on to it until tomorrow.
I think there was maybe Joan can comment also. No, maybe not Joan. Or at least maybe Monica, that there was a series of papers by VJ, the way they analyzed this multipartite entanglement. And I think even for GHZ, for 3 parties, there's certain problems that you cannot really geometrically realize that. I don't know, Monica, if you want to add something. Or...
portrait. I don't want to talk about it yet because it's coming out soon, but if you want to know, I can talk in private.
More advertisement.
Okay, so I want to do a couple of other examples for intuition building. I mean, I hope this convinces you that this is a pretty natural condition that sort of captures what's going on with the bulk entanglement and how the bulk entanglement contributes to the boundary entanglement. It's not a point particle example, but so what happens if you have an island? So that's a situation where when you look for the quantum extremal surface, by the way, one thing I forgot to say, of course, what I'm talking about here is not technically the quantum extremal surface formula, but the quantum minimal surface formula, which is because I'm on a static time slice. And it's just like the HRT formula implies the RT formula on a static time slice, the quantum extremal surface formula implies the quantum minimal surface formula via quantum focusing, same kind of argument. Yeah. Just to say that it's not technically the quantum extremal surface formula. Anyway, again, at the static level, it can happen that your QES or your quantum minimal surface actually has like a disconnected part, because it may happen that this region is very entangled with stuff here in terms of the bulk fields, so that you actually get a smaller total, even though this increases the area. If it decreases the bulk entanglement term, the second term, by enough, then this may be the minimal configuration. So what does that look like from the bit thread point of view? Well, clearly you have a lot of bulk entropy in here. So you're going to have a lot of threads that are going to be ending in this region. And then those threads are necessarily going to be coming out of the island. Okay? So, in addition to whatever else you have going on. Okay? And again, in a simple situation like this, what you can imagine is that there's a subterranean connection between these two, and then what the threads have done is that they've actually just tunneled under and come back up here and continued on their way. Okay? And then the last example I wanted to do was the, well, okay, so one, I mean, maybe it's not that interesting, but just as a very zeroth order sanity check, is that you do recover the classical formula in the appropriate limit, namely if S of R becomes negligible, this becomes 0, and if it's true that the integral over every region of the divergence is 0, then that means the divergence is everywhere 0. So you do recover the classical formula in that limit. A more interesting limit is the induced gravity limit. So in that case, S gen actually just goes to S bulk. In other words, the area term is the one that disappeared. It's opposite of the classical limit. Okay. And basically, so basically 1 over 4 g Newton has gone to 0. So what the heck is happening in that limit? Well, you have a very funny situation, because if you look at your divergence bound, I'm sorry, if you look at your norm bound, which we still have, it just went to 0. So it means your V is everywhere 0. So that seems very surprising. So what we'll do is we won't take the strict limit where 1 over 4 g Newton is 0, because that's too confusing. But we'll just take it very, very, very small. And then we'll remember that out near the boundary of ADS, you have a ton of space. Okay? I'm just giving a qualitative discussion here, but the idea is that the threads will be able to go in a little ways, and then they'll be sort of stopped in their tracks. But luckily, they can then tunnel, because you can have a non-zero divergence, to the other side. So so it's just going to look like this thing, where the only threads you have are out near the boundary. Okay? Now, how many threads can you put in? Well, basically, for every region, among the regions that you would be testing here, is a region that is homologous to A, so some region like this. And you would simply say, well, the total divergence, which is the number of threads, every thread you put in has to end within this region, because they just cannot penetrate into the bulk very far. So they're bounded above by S of R. And the strongest bound is the smallest S of R. So you reproduce that it's just the minimum of S of R. So in this limit, S of A is the minimum over R, homologous to A, of that bulk entropy. So every region homologous to A gives you one of these, gives you a bound, and it's the smallest one that's going to be the one that gives you the actual value. So you reproduce what you knew to be, basically you reproduce this formula. Okay, actually that argument is a little bit too, so that seems like a very simple check. Okay, that argument is a little bit too quick, because I've got all the other R's. This here, I'm not just saying the R's that are homologous to A, but I have to impose this on every R. So in particular, maybe there's some something that looks like this that bounds the amount I can put here And then this guy is going to bound the amount I can put here, and maybe together it's going to be less. So it seems a little bit dangerous, but luckily we know that S of A is less than the sum, less than or equal to the sum of S of A1 and S of A2. And so subadditivity comes to the rescue and says that no surface like this is going to put a more stringent bound than the ones where you just consider the whole thing at once. So this argument is actually, this works because of subadditivity of the bulk fields. And actually, when you study it more carefully, you actually even need strong subadditivity to make that work. And one thing I didn't mention, but this statement here, this theorem, as suggested by this example, requires, this theorem requires strong subadditivity of the bulk fields. If you don't have, if you're, I mean, as you would expect, everything kind of goes haywire. If you try to just formally, if you just say, oh, I'm just going to apply this formula, but I have some function S of R, that's just some random function I made up and that doesn't obey the properties that we know that entropy has to obey, then you get all kinds of weird, nonsensical results. So I think that's a nice check. So somehow this formalism knows about things like strong subadditivity. It's sort of built into the whole thing. Okay? And in particular, in the induced gravity limit, you really see that very clearly, that you would be completely screwed if your bulk entropy did not obey subadditivity and strong subadditivity. It would just not work at all. Okay? Okay, so I think those were the examples I was going to go through. And I see it's just about lunchtime. I'll just say one other thing, which is, I think, a little bit intriguing, which is that actually you can redefine, there's a different definition of a quantum flow where you simply add these two constraints. So you can say, quantum flow prime says for all R, the integral over the boundary of R of the norm let me just see how this was written, sorry. Plus, yeah, that's right, plus integral over R of the divergence of V sorry. Okay. So if I add the left and the right hand sides, then I get S-gen, right? Here, if I just add 1 over 4G Newton times the area plus S of R, that's S-gen. So if you simply add the terms and then require that to be less than or equal to S-gen, then this also works, and this is cutoff independent. So in everything I've been talking about so far, you have to make a choice of cutoff because you need to separate this term from this term. But really, that separation is totally artificial. The only thing that's really well defined is S-gen. And if you write it this way, then you get to write your whole bound. Instead of having two separate ones, you just have this one bound in terms of S-gen. And it's not at all obvious that, I mean, normally, if you just add two constraints together, that's not equivalent to the original thing. So it's surprising that it works, but you can show that actually this works. Yes?
To compute SGen, we need to impose the answer as a part of the constraint?
We're not computing SGen. SGen is given to us. It's part of the input of the QES formula.
What's the output?
S of A, the boundary entropy.
Oh, okay. Sorry. I got.
Little r is a bulk region.
Uh-huh.
And so this is SGen of the bulk region. And then this is a constraint on V. And then you just, I didn't write it, but you just maximize, well, I wrote it here. You maximize the flux through A subject to this new constraint instead of subject to this constraint.
Oh, okay. Sorry, and I have a second question. The units are not the same in the two terms that you're adding. Because you have two derivatives in the divergence and, oh, sorry. You have you have one derivative in divergence.
This is an integral over the boundary. So this integral has one less dimension than this one.
Oh, okay.
But the integrand has.
Okay.
Yeah. That's all. I'm done.
Hi, one question. At the beginning, you mentioned that with the minimum area seems like a unique surface, then we have some, I would say, freedom more than ambiguity in this approach. I thought you were going to exploit that at a certain point, and perhaps a connected question with the freedom that you mentioned. You draw some of diagrams. Can it be removed? For example, demanding that if I start in A, then I need to go all the way to AC, and I need to cross the red line at some point. Like, or would you rather keep that freedom and exploit it somehow?
Well, so you can fix the freedom in various ways, like the kind of thing you were saying, where you could just eliminate, anything that's not going from A to A complement, like get rid of that. One nice way that you can actually fix it and get a unique flow is instead of fixing one boundary region, you have a whole family of them. And then you say, I want a single flow to compute the entropy of every member of that family by the flux. So you say the flux of the flow over every boundary region in that family has to equal its entropy. You can't do that in general, but you can do it as long as the regions are nested. So if you have a one parameter family of a continuous family of nested regions on the boundary, then you can actually find a flow, and then it'll be unique because you've basically used up all of your freedom, that computes the entropy of every single member of that family. So that's a kind of a nice gauge fixing, if you want, that people sometimes use for certain purposes.
Okay, but so far then it's not something that we can exploit either. It's something that it's lying there.
Yeah.
Okay, thanks.
Okay, any further questions?
On relative entropy?
Or subregion duality, like can you put some comment like on how it looks here?
Okay, I don't have anything really deep to say about, but okay, if you look at this picture, you can arrange it so that all of the sinks are on one side of the QES, and all of the sources are on the other side. And then it starts to look a lot like connections between the bulk and the boundary. And so I suspect that, so far that's just an observation, doesn't prove anything. But I would like to say that that has something to do with bulk reconstruction. Because, of course, bulk reconstruction is really a quantum statement. It's really meaningful when you start to include the quantum corrections in the QES, because it's the quantum part of the relative entropy of the boundary relative entropy that equals the bulk one. So, so indeed, it's the quantum bit thread formula that should know about this connection. And to me, it looks like some kind of connection between bulk local operators and the boundary. but it's just like at the level of a picture. So it would be great to make that somehow more more precise.
Thanks.
Okay, any questions? Okay, so let's thank Matt again.